Hello, welcome, good morning. So today we will be doing, or rather, going to start a new chapter, rather, a new topic, which is a which forms as if a very integral part of chemistry itself. Now, we know that atomic structure, the bonding, it do form a very important part of chemistry. But this chapter is also a very important one when it comes in terms of studying chemistry, or whenever it comes in terms of that we need to understand chemistry, or we need to understand the properties of those things. So properties of those things means we need to understand the properties of elements and how it behaves and all the stuff. So this chapter is dealing exactly, or actually deals with those particular things. Now, probably you might have guessed very truly by looking at the picture, which you can see just now. That is basically, this chapter is all about the periodic table. Of course, this chapter is about periodic table, and we all know that this table is how much important this table is. How much important this table is regarding when it comes to chemical analysis, or when it terms of that properties of elements and all, the behavior of problem rather behavior of elements and formation of compounds and all this stuff. So let's get started with the periodic table. Okay, obviously, when we are having the first with the table itself, the first question that comes to our mind, that what's a periodic table? That's the very first question. It's obvious that whenever we are having a new topic, a new thing, what is the topic is all about in general, but what the topic says. The topic basically, by the word itself, you can make it out. Periodic table means it'll definitely a table. Of course, it's a table. But in that table, what is available in that table? Elements are present, and what that elements. But since elements are present, but it's not written elemental table, it's written periodic table. Yes, of course. A periodic table is it's actually the reflects the recurrence, the repetition of properties of elements after a certain intervals of time. Now, is it time over here? And it's basically after a certain interval, a fixed interval, those recurrence, those properties of elements will be repeated. So as it said, it's a table in which elements are arranged in such a way that the chemical properties becomes periodic. We all know the meaning of the word periodic itself. That periodic means repeating of certain properties after a certain period of time. So that's basically what we call as periodic. So fixed intervals of time. So those particular properties, mainly over here we concern about the chemical properties, but sometimes physical properties also, but mostly chemical properties. Chemical properties, we all know that what chemical properties means reactivity. Reactivity means how it reacts, how it interacts with other elements, other ions, how it forms molecules, and what type of formulas, what type of compounds it will form. But definitely, all those things will be repeated after a certain point of time. That's what we call as the periodic table in simple words. Now, this approach will also get changed after when the modern slightly changed when the modern periodic table will come into existence. This is just about the general definition. Now, coming to the periodic table, just apart from the general one, carrying on with the general thing, that is the first, how the elements basically, when definitely we are having the table itself, how the elements gets arranged. So we are having just how we will place how we will place, or how the elements are placed inside the periodic table. That's another more obvious probable question, which comes up. Arranged horizontally and not vertically. Just remember this. We are having. We all know that we are familiar with whenever we are having a table, we always do have that rows and columns, right? Whenever we are having a table, we are always having rows and columns. That's a very common property of a periodic table. But so with that, when we are having the elements are actually arranged along the rows rather horizontally and not vertically. So vertical arrangements are not considered. Now, these columns are basically called groups and the rows are termed as periods. The point is, now probably it is much more becoming much more clear that probably I hope you will be able to relate how what the name of the chapter itself, how the periodic table name comes up. So the arrangement is done horizontally, and the rows are termed as periods, and the columns are called groups. The rows are called periods, and the columns are called groups. Okay. So since it's arranged along the elements are arranged along the periods. The elements are arranged along the periods, and as along the period, the repeatability or the recurrence of the reoccurrence of the properties of elements do pop up. So definitely, so along the period, the periodicity is maintained, or the properties becomes periodic. Hence, and it's happening within a table, and thus it's called a periodic table. So it's said that the chemical and the physical properties becoming a periodic function of elements along the period. Hence, the name periodic table. Once again, you can just go to chemical and physical properties becoming a periodic function. Don't get confused with the word function. It's basically one type of parameter or dependent. So this is how a periodic table looks like. Okay, this is how a periodic table looks like. As you can see, the elements are arranged over here, and a lot of elements are over here. That's arranged over there, and you can see over there. There's the boxes over there with different colors. One of the things you are having that green box. The green boxes over there, mostly that's vertical boxes. Those are basically groups. Those green boxes to highlight. So the vertical portions are called the groups, and the horizontal orange boxes, what you can see, those are basically periods or the rows. So those are basically the periods and the rows. So hence, that's called the columns and the groups and the periods. And once again, I repeat the definition as it goes: it's chemical and the physical properties becoming a periodic function of elements along the period. Hence, the name periodic table. All right. Okay. Now, obviously, when we are going through this periodic table, there's a very obvious question that so many elements, so many of rows, or rather groups of periods, and the properties, and so many things we need to study. And the point is that why we need to study, right? This is the point, that why periodic table is so important. Why we'll study this one? Another quite obvious question. Now, answer to this question, that what's the purpose of studying the periodic table, or why this is so important? That is the first point, of course, that in one particular section or one particular row, we'll get the information of all the elements. So it displays all the elements at one place, or discovered till date, that are discovered. So displaying of the elements at one place, discovered till date. So that's one of the important criteria, or important point, which periodic table is accompanied with. So completely, and another one is completely arranged. The second point, the second point is it's arranged. As I said, it's not only arranged scattered way. It's arranged in a very sequential manner. So it's a very sequentially arranged elements which are placed within the table itself. So the discovered elements are sequentially arranged and grouped in terms of common properties of the elements. Probably you have noticed there is a word called common properties. common properties, definitely. As the first, it said the word is periodic, so it's grouped in terms of the elements are grouped in terms of the common properties, and definitely not placed in one particular place. Grouping means it is not it's given, the elements are not given in the same particular positions. They're given, they're having different it's a very vertically the group wise. So since it's grouped in terms of, so it comes one after the and one after the other. And definitely when it comes to one after the other, so it is after a certain point of time, after a certain what should I say, after a certain crossing over the certain elements, then definitely there is a chance that the properties of the first element from which we started will again come back. Okay, so these things, that properties will again come back after a certain point of time. Point of time means from suppose we are having the starting from one particular element. So after the elements which are present in those elements which are present in that the group of those particular element, well, again after a certain point of time another element will have some same properties. So based on that it becomes periodic. So and definitely it's sequentially arranged. So on that perspective, it is, this periodic table is important. Now it is important, we are having this, for that reason the displaying of the things, but the discovered element sequentially arranged. But will that be fair enough to conclude or to say that the origin or that for this particular purpose only, the periodic table was designed? It is, I will say, it is partially correct, but the first idea was not exactly to have the elements were arranged, rather the concept which popped up through in the minds of the people who designed this table, with that it will be we need to have elements in sequential manner. No, it's not like that. It has been the birth of the periodic table. It happened because there are a number of elements which are there discovered so far till date, and during that time, so scientists around the world were getting confused, or rather forgetting, or rather having no idea about which elements are there in the rather having discovered so far, because as we all know, the communication system during that time was not so much well popular, and hence so it was scattered, and for that reason, so it became very necessary that everybody should have an idea about which elements are there existing on this earth, and which elements have been discovered so far, and what are the parameters, what are the parameters of what should I say, parameters by which the elements differ from one of the other element, and what are some of the properties of those elements. So all these things, if it is present in a one particular place, then it will be helpful for all the scientists around the world during that time to carry on with their own experiments and to figure out some other experiments, some other approaches for that reason. So that led to this was the foundation or the background behind the starting of the process of making a table, or making our listing of elements in a one particular place. But definitely during that time, it was not, the name was not periodic table. Okay. So it started with Daubernaire. So this person started to design, or rather started to list out the elements one after the another. But the point was that how the elements will be listed in a random way, in alphabetical order, or any other things. Now the concept was that if it is in alphabetical order or any other methods, rather alphabetical order or by name itself, then it will be slightly difficult, because with time definitely they were also of the opinion, they also had that idea that with time, with more new elements will come out, will be discovered, then what will happen? So they need to figure out a method by which if one element information or two elements information are there, then rest of the elements information will also be there, or can be predicted at least. So Daubernaire did he basically classified elements in groups of three. In groups of three, whatever the elements were available during that time. So considering those elements, and based on those from those elements, whichever the elements were having common properties or similar properties, those elements were taken together and formed a triad. Triad means a group of three elements. And he noticed, and he showed and noticed also, that is, this triad was basically that the middle element and those elements, if they're sequentially arranged, sequentially means in terms of atomic masses. So that was the point. In terms of atomic masses, when they were arranged, the middle element was basically, the atomic mass of the middle element was actually the arithmetic mean of the other two elements. Arithmetic mean of the atomic masses of the other two elements. This was the observation of Daubigner, and he showed that one also, that the atomic masses of the middle element of a triad, I've explained what triad is. So with similar chemical property, I saw that one, that they are having similar chemical properties, is the arithmetic mean of the atomic masses of the other two elements. This was Daubigner's concept. So if I go with an example, then Daubigner actually, one of the triad is lithium, sodium, potassium. And the atomic masses, lithium 7, sodium 23, and K 20 and 39. So if we go on with the calculation, then definitely we'll conclude with the atomic mass of sodium, that's the middle element, which is of the triad, is having an atomic mass of 23, which was exactly matching with that, or that was the reality. Similarly, another triad, if considered present of the Daubigner triad group, then calcium, strontium, barium. And if we calcium is atomic mass 40, strontium 87.5, and barium 137, and if we carry on with our calculations, then definitely we'll end up with 87.5 with strontium, which is the middle element. And as per it's going with the Daubigner predictions or Daubigner theories, it is true. It is absolutely true. But there lies a problem. There was a problem. With this classification of the triad formation, Daubigner was successful in predicting, rather in classifying elements or grouping elements based on certain properties, and many elements were grouped also, but it also failed. Daubigner triads failed. Why it failed? The first is the rule was unable to form the triad with all the elements existed during that time. That's the first point. That's a very important point, that Daubigner was unable to form the triads with all the elements existed during that time. So only few elements or some of the elements were considered, and not all the elements were considered in this triad, or was unable to put it under this triad rule, and hence it failed. For example, if we are considering this triad, so nitrogen, phosphorus, arsenic, and if you calculate, we know the atomic mass of nitrogen is 14, phosphorus 31, and arsenic is basically almost in the 70s. So unfortunately, if we calculate the atomic, the mean of the atomic masses of nitrogen and arsenic, then it will not end up to 31. So that's an erroneous. So this triad rule was not, or rather, is not valid for this particular triad. Fluorine, chlorine, bromine. This one also the same thing. It's not. So fluorine is 19, chlorine 35.5, and bromine almost 79. So if we calculate the mean of the atomic masses of fluorine and bromine together, then we will not end up to 35.5. So since we will not end up to 35.5, hence triad rule becomes not valid. It becomes invalid, of course. Okay. Now, following this scenario of the triad, of the triad rule, another scientist, he now proposed his theory. He also considered the similarity was he considered the atomic masses of elements, but his theory was. This theory was the elements are arranged in an increasing order of atomic masses. The properties of 8th element is similar to that of the first. This was basically given by Newland, and from the J.R. Newland, a British chemist, and called the Newland law of octaves. As you can see, it's called the Newland law of octaves, and what it states that when the elements are arranged in an increasing order of atomic masses, previously also increasing order of atomic mass, that was a sequence of the triad also, over here the same thing. The only thing, the properties of the eighth element, so over there they form the triad, but over here it's not the triad rule is not there, so there is no grouping of such 3 or 2 elements or rather 4 elements. It is basically arranging the elements in increasing order of atomic masses, and Newland observed that the certain properties of the elements which are in common actually came back after 8 elements, rather 7 elements. So start from the starting point after 7 elements, so we'll get back the same property from where we have started. So if element A, for example, if element A is having certain properties, so those properties will be again repeated, or similarity, very, very similar properties will be again repeated once again when we will travel from that particular point up to the 8th element. We will get back the similar sort of properties. So this observation was made by Newland, and he proposed his theory in 1865. Now, this Newland theory also failed after a certain point of time. Though with this, if you consider the elements like lithium and sodium, beryllium, magnesium, you will always get that that repeatability is considered with the first element and the 8th element. So beryllium first, 8th element is beryllium. Magnesium with respect to beryllium. So there is a repeatability of properties, but it also failed. Why it failed? The first several elements were made to fit in the same slot of Newland's elemental classification. There was a problem, and there was a big. The problem was that Newland considered, based on similarity of properties, Newland just forced some of the elements to stay in one particular place. So one particular room is being shared by 2 or 3 or 4 elements together, and those elements were not actually having very similar properties. Only very few properties are similar, otherwise the rest are no way similar, but still they are being placed in the same particular space of the table. The next, we are having the elements with dissimilar properties were also grouped together. So that's another blunder Newland made, unfortunately, that Newland also, elements with dissimilar properties, they were also grouped together. So when Newland's table was prepared, it was observed that halogens and that metals like cobalt, nickel, all those metals were also grouped together, where halogens were basically gaseous and cobalt, nickel, they were metals. They were having their good conductors. Halogens are bad conductors of heat and electricity. So there are a hell lot of differences in properties, but still they were grouped together. That's a big blunder to the Newland's table of elements. Now, another problem was elements with atomic masses greater than 40 failed to comply the rules of the theory. That was another problem. So this actually gives the information and an idea that Newland's laws were basically applied to, or rather is applicable for elements up till atomic number, or rather atomic masses up till 40. So those elements having atomic masses up till 40, for them this Newland's theory is applicable. But for the rest of the elements, that means elements with atomic masses higher than 40, will not be able to satisfy, or will not be able to apply, or this theory is not useful for them. Newland's table did not have room for newly discovered elements, and that remains secluded. That's a very, very big problem. Now, Newland should have understood that understood that there can be some other elements, but unfortunately he didn't mention or didn't leave any space within his table for assisting or to accompany new elements new elements which can be discovered in the future and that can be accommodated within his table. So what will happen? Definitely the Newland's table, or the elements which will be discovered later on, will remain secluded, and they cannot fit they cannot find their space, or they cannot find their positions, or within the particular, they cannot find their positions or their specific place within the particular table of Newland. And what will happen? Definitely they will remain secluded. They will not be considered within the table. They will be considered as outsiders, and hence they will not be a part of that particular elemental table. So these things led to the failure of Newland theory of arranging elements. So with the failure of Newland's theory, there came a time, there came a demand for an upgradation or some new techniques or methods by which this particular arrangement of the elements can be made. Thus, a Russian chemist, or rather he was a physicist come chemist, or maybe a Russian chemist named Dmitry Mendeleev. So this person, once again considering the same common scenario, common parameter, that is, if you consider the Newland also, it started with not Dauvergne. So Dauvergne actually considered that atomic mass of the elements for arranging the elements. Newland also considered the same thing considered the atomic mass for arranging the elements, and Mendeleev also did the same thing, considered atomic mass for arranging the elements. So what he proposed was the physical and the chemical properties of elements, also compounds and its formulas, are periodic function of their atomic weights or atomic masses. So what if we compare between Newland and this Mendeleev's table of elements, Mendeleev's table of elements, the slight dissimilarities, they both consider that the physical and the chemical properties of elements are periodic functions of atomic weights, and Newland said that these things will be repeated for the 8th element. So this was slight change. This was the slight change which Mendeleev made in his table of elements. So since the periodic functions or the periodicity of elements are coming over here, and hence the name was periodic table. So it's called the Mendeleev's periodic table, and thus it said that the physical and chemical properties of elements, also compound and its formula. So it's not only chemical properties of elements, considering the compounds formed by those elements and the significant formulas are periodic functions of their atomic weights or atomic masses. So it will depend upon. So the point was, it will depend upon the atomic masses and or anything else. So no 8th element or 2nd element or the 4th element, it's just an element. So after a certain point of time, it will again recur. So whatever the element will come, it will come. That's the basic logic. So example, you can see lithium, sodium, potassium, beryllium, magnesium, calcium. So it's a repeatability or the recurrence of properties of the chemical and the physical properties. So if you consider lithium is also a reactive metal, sodium is also a reactive metal, both are highly reactive in nature. So the reactivity considers like this. Sodium is it's a very considering having distribution of atoms, the similar set of distribution are also present in lithium. So it goes like that, where it seems the products from the sodium is similar with the products from the lithium. So it's a very, very similar sort of properties, chemical as well as the physical type, recurring after a certain interval of elements. That's periodics. Okay. Now, from this particular definition, or rather this statement of the Mendeleev's periodic table, what to conclude? The conclusion is basically that if the elements are arranged in increasing order atomic masses, then the elements with similar properties should recur after regular intervals. That's the basic logic of the conclusion that we can draw from this Mendeleev's periodic table. Okay. Now, Mendeleev's periodic table also failed. There was also certain problems within the Mendeleev's periodic table to the failure of the Mendeleev's periodic table. Now the point is, what are the reasons? Some few reasons were there. Number one, the position of hydrogen. This position of the hydrogen element, the place where hydrogen has been positioned, there is a problem with, because hydrogen is basically positioned in group 1, but in group 1, the first group, is the elements of the first group are in no way similar, having no similarity in properties with if we are considering the elements of the first one. So lithium, sodium, potassium, they are having no similarity in properties with respect to hydrogen. So that's all our metals where hydrogen is a non-metal. So that's a very, very big problem with the position of hydrogen placed in the in Mendel's periodic table in group 1. The second, we are having the variable valency of elements. The Mendel's periodic table didn't mention or have no consideration of the variable valencies of elements, but it's true. The elements do depict variable valencies, but how to represent, how to explain those the variable valencies of a particular element, it cannot be understood by generally by Mendel's periodic table. The second, we are having position of isotopes. Isotopes were not considered in the Mendel's periodic table. That's another problem. So where the isotopes will be positioned, there was no mention, there were no consideration, there was no declaration made in the table that where isotopes will be positioned. That's another problem with the table, and which led to failure of Mendel's periodic table. So with this failure, definitely, since as I said before, that Mendel's periodic table actually led to the foundation stone of the modern periodic table, and thus the modern periodic table came up. So position of lanthanide is another one with a failure list. So modern periodic table, now it came up. The modern periodic table says that the physical and the chemical properties of elements are the periodic function of the atomic numbers. Now that's a very a revolutionary point of difference between the rest of the periodic table considerations and the modern periodic table. That if you consider it that Daubeney and Newland, followed by Mendeleev, in between some other people who were also there. So those people always considered the atomic masses, but in the modern periodic table, they consider that periodic properties and elements are the physical and the chemical properties. Those properties are basically periodic function of the atomic numbers. So it's no more the atomic masses, but it's basically the atomic numbers. And hence, if you follow the modern periodic table, you will see the elements are basically arranged in terms of their atomic numbers and not in terms of their atomic masses. Okay? Because if it would have been so, then argon would have not been placed before potassium. Okay. So what does this mean of the statement in general? If the elements are arranged in increasing order of atomic numbers, then elements with similar properties should recur after regular intervals. It's simple, just similar to this. In place of atomic masses, it's got changed with atomic numbers, and the rest remains the same. After a certain point of time, with respect to atomic numbers, similar properties will come back, will recur. Okay. So after so much of analysis and studying the information, definitely once again we'll go through the periodic table or the modern table, how it looks like. This is how the modern periodic table looks like. And though you are seeing that hydrogen in the first column over there, but actually it's not being placed over there. That's a different point. In the modern periodic table, this hydrogen is actually placed in a separate group. This hydrogen is placed separately. It's not considered as a part of the first group. Okay. So as per the modern periodic table and the latest periodic table, you can go with that. Over here, you can see a lot of colors are there, and those colors are actually representing certain groups. So the first group 1 is being considered. Group 1 is being given the red color, followed by orange color to group 2, then followed by if you go to the other middle elements, they're having different colors. Then group 3 there is a metalloid section which are marked with yellow. The non-metal section which are marked which are marked with green, and the inert gas section is also there, which are marked separately, and as well as you can see the lanthanides and the actinides with the symbol La, that's the lanthanum, and actinium AC. So based on that, it's all the elements are over there. So we can you can see those things rather prominently. How it has been represented. How it has been represented. Now, with these elements, with these elements, you can see there are a lot of information given that if you see that atomic number, and as it said, that atomic number is an arrangement, the elements are arranged in terms of atomic numbers, and hence if you notice that all the elements are in this particular this periodic table are basically represented by symbols, and at the bottom it's the name of the element is written, and the atomic mass of the elements is much smaller, written much lower than that. And at the top of the symbol, you can see certain numbers, 1, 2, 3, 4, 5, 6, whole numbers are there, not decimals. You can see decimal places or decimal numbers with atomic masses, but not with atomic numbers, you can see. So those are placed at the top. So that's basically a general way of representing elements within a periodic table. Because as it said, it is arranged in terms of atomic numbers, and since numbers at the top are actually being focused earlier compared to numbers at the bottom, and hence it is the atomic numbers are placed at the top. Atomic numbers are placed at the top within different groups and periods. Now the question arises that apart from, if you're saying that which elements, atomic number 2 or atomic number 3 or atomic number 50, whatever. So in terms of atomic numbers, it becomes it's a very general, straightforward question of categorizing or identifying elements, or which element I want to specify. That's a very obvious question, or obvious way. But if you are interested, that the point of the question is there any other method that elements can be identified apart from mentioning the atomic numbers? I'll definitely say yes. And that basically that thing I've basically termed as the element signature. The element signature is basically, I've given this name as if that as another way of an element can sign, or I can also say as the elemental coordinates. We are all familiar with geographical coordinates, latitude and longitude. The point of intersection of latitude and longitude gives the place, the required place. The same thing over here. The point of intersection of a group and a column, and a period. The group and the period. The point of intersection of a group and a period gives marks that a particular element. So, for example, if I consider the table provides exclusive position to individual elements. For example, if I consider sulfur, then group period 3, group 16. So if we go along by that way, then the point of intersection of group 16 period 3 will be element number 16. Now group 16 is also known as group 6A, basically. It's 6 written, but still it's 6 given, but it's called group 6A. Similarly, if you're having another element, for example boron, will have as per the modern periodic table, atomic number 5, it will have period 2 and group 13. So it's a point of intersection of the individual groups and periods, from where we can get the elemental coordinates and to identify, to mark a particular element within the periodic table. So in that way, the elemental representation in the periodic table, it's generally, as I said, it's done with the atomic number at the top and the atomic mass at the bottom. So what's the purpose of? So we also know that atomic number at the top means, since the periodic table is arranged in terms of atomic numbers, so definitely it's written at the top because the top numbers are more easily readable and become more vibrant. But the general convention of writing a particular element or representing a particular element is like this: or element X with Z, that the atomic number at the base, at mass number at the top. That's just the reverse, that's the opposite to the reverse way as written in the periodic table. Okay. Now, as you can see, lithium with 3 and 7. Now, what's the reason for this, of writing this way? Basically, since we're over here in this modern periodic table, there is a consideration of the position of isotopes. Consideration of the declaration of the isotopes, and we all know, since isotopes vary in terms of atomic masses and not the atomic numbers, so to distinguish it becomes easily to read and to identify, instead of subscript numbers. The superscript numbers are easily notable, and hence for this reason, for isotopes, this convention, the mass number is written at the top and atomic number at the subscript. So superscript and a subscript, like that way. So when we are having these groups, basically, when we are so with these elements and they're arranged in groups, as I said, these groups are basically having certain names. And as I said, group one is as group one is called group 1A, group 2A, group 3 or 13 or group 3A, and if I go group 1 is called the alkali metals, group 2 alkaline earth metals. So group 1 alkali metals and group 2 alkaline earth metals. Following group to group 4 is called group 14 or group 4A, group 5, group 15 or 5A, and these elements are also called pnictogens. Remember this one? So group 5 elements or group 15 elements, 5A, group 5A or 515 or group 5 whatever, group is called a pnictogens. Group 6A or 16 is called the chalcogens. Group 17 or 7A or 7 is called the halogens. And group 8 or 18 is called the inert gases. Or it's called 8A rather. So there is a very interesting thing about this particular groups and this group A, that is in terms of their valencies. So if you notice the valency, it's basically group 1 is having valency 1, group 2 valency 2, and similarly group 3 valency 3, group 4 valency 4. Once again, group 5 valency 3, group 2, 6 valency 2, 7, 1, and 8, 0. So you can see there is a trend. I hope you can understand the trend. That's 1, 2, 3, 4, 3, 2, 1, 0. There is a trend like that way. Okay, there's a trend like that way. So it's first increasing, once again decreasing. So what are the perspectives of analysis? Perspectives means in terms of the this periodic table is analyzed in terms of group and in terms of periods. Now in terms of periods, I also consider that along the period, it's called from left to right of the period. It can be from right to left of the period. So it's very important when you're mentioning regarding when you're studying this of any variability, that's how it goes like that way. That is whether it's from right to left or whether it's from left to right. So anything is possible. So that's very important because from every side this the parameter gets changed. Similarly, group wise, we're having from down the group or up the group. So it's very important. So in what perspective you are stating or analyzing a particular parameter of within a group or within other elements. So there are a list of periodicities. That means based on which, so what are the parameters which are considered to be in this periodic table? That's basically the first is called the nuclear charge, whose variability we study. The valency is variability we study. Then comes the atomic radius, which we study. The variability we study in terms of period, in terms of groups we study. The metallic character we also study. Followed by the metallic character goes the ionization potential, followed by the electron affinity and the electronegativity. So these are the certain periodic. It's not that only these properties are there are other properties are there also, but for this particular time, or rather for this class, or this periodic properties will be considered, or they will be analyzed, evaluated. Okay, so that's all for I'll just put a break over here with today's lecture, and I hope these things becomes clear to you. So if any confusion, anyone, you're free to ask questions, and you feel free to contact me anytime, anytime you feel like. So that's all for today's lecture. I hope you have understood that once many things have got clear to you. If not, free to ask questions. So till then, stay safe and take a very good care of yourself. Thank you so much.